Today, we're putting on our detective hats and cracking a real scientific case, the mystery of an unknown density. But here's the twist, right? It turns out one of our most important tools might actually be, well, sabotaging the whole experiment. Let's dive in.
So first things first, what even is density? You can think of it like a substance's unique fingerprint. It's the secret sauce behind why some things float and others just plummet. It is a truly fundamental property of matter, and you know what? By the end of this, we're going to have it down cold.
I mean, have you ever really thought about how a gigantic 200,000-ton steel ship can just float? It's kind of wild, right? Steel is way, way denser than water, so it should sink like a rock. And the whole secret is in the shape. It's a super clever trick of manipulating density that keeps these massive giants from ending up at the bottom of the ocean.
At its core, density is just how much stuff is packed into a given space. That's it. It's the measure of an object's mass crammed into its volume. So the more tightly you pack that matter in, the denser the object becomes. Simple as that.
And this is the key to our whole investigation right here. Density equals mass divided by volume. D equals M over V. It looks so simple, but believe me, this little formula is incredibly powerful. It's what's going to help us unlock the secrets of our mystery substance.
Okay, check out this lineup. You've got gasoline, which is less dense than water, so of course it floats. But then you have lead. Totally different story. It's an absolute heavyweight, packing a ton of matter into a tiny little space. Every single substance has its own unique density. Like I said, its own fingerprint.
And here comes the plot twist. We've got our mission, we know what we need to do, but there is a huge obstacle standing right in our way. It all comes down to a problem of precision, and if we're not super careful, it could derail this entire investigation.
So, the mission, should we choose to accept it, is to find the density of an unknown salt solution. To pull this off, we need two things, and they have to be accurate: the mass and the volume. Getting the mass, that's the easy part. But the volume? Well, that's where our real mystery begins.
All right, let's meet our tools for the job. First up, the analytical balance. This thing is a master of precision. I mean, it measures mass with incredible accuracy. And then we have the volumetric pipette. This is our prime suspect. It's labeled 10 milliliters, but it's hiding a little secret, a secret that could ruin everything.
And here's the heart of our problem. See, the pipette is labeled 10 milliliters, but the fine print, the source material, tells us it could be off by a little bit. It might seem small, but that tiny error is more than enough to throw off our whole calculation and give us the wrong density. So plain and simple, we just can't trust the label.
So what do? What do scientists do? Well, they don't just throw up their hands and give up. No way. They use this really brilliant workaround to figure out the pipette's true volume. This right here is the beauty of the scientific method in action. You take a problem and you turn it into a super clever solution.
So here's the puzzle we've got to solve together. If we can't trust the number printed on our tool, how in the world do we find out its exact volume? How do we take this unreliable suspect of ours and turn it into a trustworthy partner for the investigation?
The answer, believe it or not, is pretty much all around us. It's water. Good old H2O is our secret weapon. Why? Because its density is a well-known, totally reliable constant. You can see on this table, all you have to do is check the temperature and boom, you know its density with pinpoint accuracy. It's the perfect benchmark, the perfect ruler to measure against.
Okay, so here's the game plan. It's a three-step process. Step 1, we take our suspect pipette and use it to measure out a sample of water. Step 2, we weigh that water using our super-duper precise balance. And then for step 3, we use water's known density and that trusty formula of ours to calculate the pipette's actual true volume. See what we did? We just completely turned the tables on our unreliable instrument. You know, this whole process actually has a name. It's called calibration. It's a fancy word for a simple idea. We're using something we know for sure, a constant, in this case the density of water, to figure out something we don't know, an unknown variable, the pipette's true volume. It's exactly how we turn our suspects into trusted allies in the lab.
All right, our tool is calibrated, our suspect has been cleared, and we know its true identity. Now we are finally ready to get back to our original mission, finding the density of that mysterious solution.
And there it is, our hero, number 9.98 milliliters. See, it's not the 10 milliliters that was printed on the side.
This is the true, calibrated volume that we figured out through our little experiment. This is a number we can actually trust, a number that's going to lead us straight to the right answer.
So, armed with our new, super accurate volume of 9.98 milliliters, we go back to our unknown solution. We measure it out, we weigh it, and boom! Just like that, we have a precise mass and a precise volume. The case is officially cracked. So, you might be thinking, okay, that's a neat little lab trick, but why does any of this actually matter? Well, it's because this isn't just about some random salt solution. This is about the very foundation of pretty much all science and technology.
What we've just walked through is calibration. It's the whole process of making sure our instruments are telling us the absolute truth. You can think of it as the bedrock of trust in science. It's the engine that drives progress forward. Honestly, without it, the wheels of innovation would just grind to a halt.
I mean, just think about it for a second. Your GPS that gets you around, the medicine you might take, even the computer you're watching this on right now, all of it depends on incredibly precise, calibrated measurements. We live in a world that is built on accuracy. So it kind of makes you wonder, right? What happens when those measurements are just a little bit off? The consequences, well, they can be staggering.